Hello, everyone. Thank you for being here, and I think it's 12:01, so we'll go ahead and get started. We have a few people that are calling in still, so we'll go through some announcements first. First of all, I'd like to thank you for calling in and participating in our 7th webinar in our free series. This series is presented by the Fluids Engineering Department at Southwest Research Institute, and I'm your host, Angel Wildman. Our speaker today is Mr. Terry Grimley, and he's going to lead us through a discussion of flow calibration of gas meters. But before we get to that, I have a few announcements, so we'll give a chance for some people to call in too. First, please mark your calendars for our next free webinar coming up on January 15th, 2019. Can't believe we're already close to 2019, it's crazy. But on that day, Joe Mariquin is going to lead us through a discussion of artificial lift test methods. Second thing is, today's presentation should last about 45 to 50 minutes, and that allows us some time afterwards for questions. And we're going to address all these questions at the end of the presentation. You'll notice that your microphone is currently muted, and it's going to remain that way throughout the presentation. So if you have a question, please email me, your host, at any time during the presentation, and we will address all questions at the end. My email address is going to be on every screen, or it's going to be on the screen on every slide. So if the question comes up, please email it to you and we'll get to you. If we don't have time to address all the questions, then Mr. Grimley will reach out to you specifically and reply to your question. So the third thing I have on here is if you've called into today's meeting and you need the meeting key to see the presentation, it's Y as in yes, 0154, and if I notice that someone's having a hard time calling in, I'll probably ask Terry to repeat that a few minutes into the presentation. If you had the system just call you from the link, you shouldn't need this meeting key. You should be able to see the presentation. So that key, one more time, is Y0154. Finally, as with all of our webinars, today's presentation is going to be available for viewing on YouTube in about 3 weeks. So keep your eye out for that. We'll send an email out to everyone that registered so that you can view it in the future or pass it on to anyone who wasn't able to call in today. Okay, so let's go ahead and get started. Today we'll be hearing from Terry Grimley on flow calibration of gas meters. Terry is our resident gas flow meter expert. He's been part of SWRI's metering research facility since its conception in 1991. And in that time, he's helped change the way that gas metering calibrations are performed and how gas flow meters are tested. Aside from gas flow meters, Mr. Grimley has professional interest in heat transfer, fluid mechanics, two-phase flow, and other mechanical engineering activities. He's participated in many projects in these areas over the years, ranging from airplane fuselage structural testing to fluid dynamic experiments on space shuttle. So we look forward to getting a little bit of Terry's wisdom today in the presentation. With that, I'll hand it over to Terry.
Thanks, Angel. What she's really trying to say is that I'm old, so that's where you get the wisdom from, is from being a little bit older than other folks. As she said, the topic for today is flow calibration of gas meters. Just to give you a quick overview of what we're going to talk about here, let me get to the first slide. First question is, why should you flow calibrate? We'll talk about that. We'll go through some flow calibration basics and talk about different facilities that are out there that are available for doing flow calibration. And then some things that you should think about as a user, as an end user, when you're going to get a meter calibrated before you send it off to a lab. By way of example, we'll look at Ultrasonic, Orifice, Turbine, and Coriolis meters, just to give you an idea of some of the things that are a little bit different for those different meter types, some considerations there, and then we'll finish off with conclusions. As Angel said, this should take 40 minutes or so, so hopefully you got a good lunch. You can snack along while I'm talking. So the first question, why should you flow calibrate your meter? Sometimes it's because you think there might be a problem with your meter. You've got a loss unaccounted for that points to a certain meter, and that's what you want to go check that meter out. So that's a good reason to calibrate it. Your tariff may indicate that you have to calibrate the meter. It may reference an industry standard like AGA 7 or AGA 9 for turbine meters or ultrasonic meters that tell you that, you have to calibrate a meter to make sure that it's accurate. You may have a custody transfer dispute. The people on the other side of the fence, maybe their meter doesn't agree with your meter, so how do you resolve that? The old joke about if you have one watch, you know what time it is, and if you have, two watches, it's an argument. So you can help resolve that argument by testing one or both of those meters. Bottom line is, most of the time, you're calibrating a meter because you want to be as accurate as possible. You want to get the right answer. And truly, when you think about the cost of the material transfer through a meter, the cost of the calibration can be extremely cheap relative to the error that you can incur if you miscalibrate the meter or you don't get the meter calibrated. By way of example, if we look at an ultrasonic meter and we say, okay, there's a bias error in the ultrasonic meter, and if that if that bias error is only 0.25%, keeping in mind that AGA 9 will allow up to 0.7% error in that meter without it being wrong, right? So if I'm at 0.25% of the meter, 0.25% error in the meter, running at half scale, 50 foot a second through that meter, and gas costs about $3 per 1,000 standard cubic feet, you can see the costs outlined in a little table there at the end of the year. That's a fair amount of money. That's 1 meter and 0.25%. Okay, there are lots and lots of meters out there. They're 12 inches a pretty standard size. If you look at that number, you can say 537,000. Well, guess what? Cost of a calibration is about a week's worth of that error. So it's good insurance. So how do you come about creating these cool metering errors? Well, one of the things that happens in the field is you can have operational effects. Clean, dry natural gas is not always so clean and dry. You can see the examples that are there on the screen of orifice plates that have been removed with obviously residual liquids, splattering through the orifice. You can also have things like overpressure of a plate. You overflow the plate so you've bent it. And then if you just have impact, like in this lower picture in the middle, you can pretty well destroy the plate there. But the errors can be more subtle too. There can be things like a gasket that just didn't get aligned properly. Someone used the wrong size gasket or let it unwind into the flow. Those types of operational issues can also cause errors. Of course, there's other nasty things that are out there. You go to inspect a meter and you find that your flow conditioner is completely plugged up with, black powder or soot, or you've had some debris from the initial startup that was in there. All these are operational issues that can cause the meter to have a problem after it's been calibrated, after it's been installed. So these would be good examples of when you might want to go back and try to figure out how much error exists in that meter as a result of this type of operational issue. There's other things, though, that sometimes you build into your station that can also cause problems. The picture on the right is a Where's Waldo kind of thing. I'll show you where the meter is in that in just a second. When people install meters, it's not always a nice, long, straight pipe. You have headers, you have elbows, you have valves, pressure regulators, filter separators, all that kind of stuff changes the shape of the flow profile. And depending on the meter type, some meters are sensitive to this and some are less sensitive to it. We'll go over that in just a second, what my take is on the sensitivity of different meters. If you haven't found a meter yet, it's right there. There's an ultrasonic meter there partway down the run. Okay, so when we're talking about a distorted flow profile, what I'm talking about is if you are to look across the pipe and measure the velocity at points as you're, say, traversing across the pipe, what you're going to find is the velocity is not uniform. It's low at the wall and it's highest in the center. In this example, the bullet shape is a little bit of an extreme. That comes from an equation. Actual gas flow doesn't form a point at the tip, but it is a fairly consistent looking shape. What's shown there, though, is the flow downstream of a single elbow. And when you are 10 diameters downstream of a single elbow, you have a huge distortion in the profile. And that's what I'm trying to show with my mouse here. And as you advance down the pipe, that profile gets more and more well-behaved and goes back to this fully developed shape at somewhere near 80 or 90, 100 diameters of pipe. You know, most people don't have 100 diameters of pipe to put downstream of their headers, and that's why things like flow conditioners come into play, because they can advance that profile so it's not just relying on the wall friction to reshape the velocity. So why does this really matter? Well, it matters because different meters are sensitive to the shape of that flow profile. One well-known example is orifice meters. Orifice meters are, the coefficients that were developed for orifice meters are based on fully developed flow or something very close to it. So if you have distortion in that flow profile, then it affects the operation of that orifice meter and you get the wrong answer. Ultrasonic meters, came along with multiple sensors, multiple path locations, and the idea there is that those reduce the sensitivity to flow distortions. And they really do, that's true. But the other thing that came with ultrasonic meters is the expectation for increased accuracy. So if you want to get your accuracy down to a few tenths of a percent, you can't ignore the fact that you might have flow profile distortions. That meter may need some help to tolerate the distortion that's in the pipe. Other types of meters that are out there that are probably a little more apparently affected by profile distortion is a pitot probe type meter. If you're measuring at a single point in the profile or even at a couple points in the profile, you can imagine that if the profile looks like the image that's on the screen there, if I'm measuring in the wrong point, I'm going to get the wrong answer. If my profile is not well developed, I'm not going to get the right answer. So that's how those are sensitive. Turbine meters, depending on the design of the meter, can be sensitive or not. Just depends on how much flow conditioning is integral to that turbine meter as to how it reshapes the profile going into the meter. Positive displacement meters, bent tube Coriolis meters, those tend to be relatively insensitive to profile distortions. A displacement meter, either a rotary or diaphragm meter, that's operating on the idea that it's displacing a certain amount of gas per every rotation of the meter. So the fact that the gas is distorted, it doesn't really matter. The meter doesn't care. Coriolis meters work on a different principle. They're exciting a tube and they're looking for that small Coriolis force that's generated when gas passes through the meter. That also tends to be not so sensitive to flow profile distortions when the tubes are bent. So again, why does all this stuff matter? Well, it matters because if you're going to calibrate this meter, these are things that you need to know. You need to know the characteristics of the meter before you decide how you're going to calibrate it. But before we talk about that, we're going to shift gears just a little bit, and we're going to talk about some calibration terminology and then calibration facilities. So uncertainty, I've got like a $100 definition of uncertainty up there, and I dumbed it down from the one that's actually out there in some of the ISO guidelines and things like that. But essentially, uncertainty is a measurement of how well you know the answer that you're seeking. How close are you to the truth in the measurement that you're doing? And uncertainty is always going to be an estimate because you don't know the truth. You can do repeated measurements and get a better idea of the truth, but you don't really know what it is. Related to that are things like repeatability. So if I do the same measurement over and over again, do I get the same answer? How wide is the scatter of that data as I'm going through those measurements? And then reproducibility is a little bit different, because reproducibility means I come back a month, a week, a year from now, and I repeat my same test, and do I get the same answer? So how, over a longer period of time, how repeatable is that data? That's reproducibility. These things matter when we're talking about calibrations, because calibrations are typically going to be multiple measurements of some variable, and we want to know whether we're measuring that variable very precisely or not, and then how close we are to the actual answer. So what I'm showing here is just a normal distribution. If you take multiple measurements, the y-axis is how often those measurements occur, and the x-axis is what you're measuring. So in this case, let's say we're measuring flow rate, and we have this distribution of points around some mean value. I'm going to point that in the middle. That's the average measurement that we get. And then if my measurement looks like the narrower band, I'm going to say that's a fairly precise measurement. So I'm repeating my measurement, and I'm getting the same values over and over again. If I do that same measurement, however, and I get a wider band, I'm going to say that's imprecise. I have an additional uncertainty that's associated with my measurement because I'm not doing it repeatably enough. Okay, so those are two kind of extreme illustrations of different types of measurements. The fun part in all of this is you don't know what the true value is. You have a measurement, but you can never actually know what true value is. Yeah, I know the hardware store says you can, but this is a different thing. So when you measure against a reference, the calibration facility provides that reference value, and that's going to be considered to be the true value, even though even the calibration facility has uncertainty associated with it. Now, if you happen to measure relative to the true value and you're off, like this is showing, so the true value is over on that red line, and my average measurement is here in the middle, then I'm going to say that I'm biased. I'm always measuring at some discrete distance away from the true value. I can be precise or imprecise in that measurement. But if my true value or my reference value is right where I'm measuring as well, then I'm unbiased, and I'm going to be fairly precise or imprecise depending on the scatter of the data. So the idea of calibration is essentially to move the measurement of whatever device you're trying to calibrate so that it aligns with the reference standard to make a unbiased measurement. That doesn't mean the measurement's perfect. It just means is that it now agrees with your reference standard. Okay, so calibrations, that's what we're here to talk about. All flow calibrations for gas, and actually anything, are really based on the same thing, and it's a conservation of mass. It's not conservation of volume, it's conservation of mass. That's important when you're talking about gas. So if I take my example here, and I've got flow in a pipe, and I stick 1 meter on one end and another meter on the other end, and I'm going to call my first meter the meter under test, and the second meter is going to be my reference meter. Each of those meters can be present at different pressure, temperature conditions. They can have different areas. They can have different velocities. That doesn't matter as long as I account for those differences between the meters, because what I want to do is I want to check the mass flow rate at each of those meters. I'm going to do that. I'm going to draw a control volume around those two meters, and as long as the flow is steady, then the equation at the top is valid, that the mass flow at one end equals the mass flow at the other. So that's a good thing. The bad thing, though, is if I don't have steady flow. So if I don't have steady flow, then the amount of mass that enters that pipe on one end is not necessarily the same amount that exits on the other end. Eventually, yes, it'll all come out the same, but if in the meantime I'm either increasing pressure in this middle area here, or I'm decreasing pressure in that middle area there, or I'm increasing temperature, that's the same difference, then I don't actually have a steady flow condition. In those cases, you either have to account for the fact that you don't have a steady flow condition, which is tough, or you need to alter how you're doing the test so that you do have steady flow. So normally calibration facilities or any facility is trying to get a steady flow condition so that they can match the mass flow between those two meters. And regardless of what type of meter we're talking about, that's always the basis for calibrations. Okay, so a few different options for how you might actually go about calibrating a meter. If you're daring, you can do an in situ proving of meters. That means you can do it out in the field. There are people that are doing this now commercially as well. And for certain meter types, that's not uncommon to do. Small meters, low pressure applications, in situ proving is a pretty common thing. AGA report number 6 describes some of the methods that are necessary to do that type of proving and some of the things that you need to consider. Essentially, it all comes down to the slide that I showed you on the previous slide. It's just mass flow. But AGA 6 also covers using critical flow devices and then proving field meters with master meters. In the flow calibration facilities, most of the time those are going to be using a master meter of some kind. And we'll talk about two different types of systems that are out there that are commonly available. One is an open type system. Essentially, that's a pipeline where flow is diverted through a set of reference meters and your meter under test as well to do the calibration. So Trans-Canada Calibrations up in Winnipeg, CZ in Iowa, Pixar in Germany, and there are others that do that type of testing. The other option is a closed loop recirculating system, and that's what we operate here at the Meter and Research Facility. And they also exist in other places. Fortis, BC has one, Force and Euroloop over across the ocean there have those types of facilities as well. They're just different approaches to doing the same type of test. When we go through this examples of the flow meter calibration, the traceability of a flow facility, one of the things that is a little different between an open loop design and a closed loop design is the ability to control pressure in the facility. In an open design facility, in general, that's going to be operating at whatever the pipeline pressure is, unless there's a special case where they can reduce the pressure for a specific purpose. Generally, they're going to be operating just under whatever condition the system is there. In a closed loop facility, because it's purpose built, because we actually have to put gas into the loop to make it work, you can test at any pressure or test at whatever pressure the facility is capable of. So depending on the meter type and depending on the application, there are certain advantages to closed loop facilities. The biggest downside of that is you have to produce all the gas flow yourself, so then it tends to be a little more expensive to generate that flow. But stepping away from that, all calibration facilities work with secondary measurement standards, and those are working standards. That's really what they're going to use to compare your meter to. In a lot of cases, that's going to be a turbine meter that's been calibrated by some other device. It could also be a rotary meter or a critical flow nozzle. At the Meter and Research Facility here, we actually use critical flow nozzles as our secondary device, and then we have turbine meters that serve as backup devices for process control. Those devices, those secondary devices that are used on a day-to-day basis, are then calibrated against some primary measurement system. That can be a volumetric system, like a sliding piston or a sweat volume. It can also be a pressure, volume, temperature, time system, PVTT system. Or in our case, we actually use a weigh tank system. We weigh gas that has flowed over a period of time. We have a mass and we have a delta time, so we can get mass flow rate. The great thing about all these calibration facilities around the world is most all facilities participate in interlab comparisons. So that kind of establishes the equivalence of different test facilities so that you can go to any of these facilities and you should be able to get a calibration of your meter that's within the facility's uncertainty statement. And that's important too because you're not always going to go to the same calibration facility for all of your meters, and your people that you're trading gas with are not going to go to the same calibration facility necessarily as you do. So it's good to understand that these facilities have done testing and continue to do testing to make sure they're essentially all the same. Okay, so calibration systems. I mentioned primary calibration system. This is an example of our weigh tank system at the Metering Research Facility. Essentially what we have is a large spherical vessel that's sitting on a scale. The guy on the right of the picture, his name is Joe. He is not a midget. He's a full-size guy. The tank's pretty big. It's about a 10-foot diameter sphere. It weighs about 24,000 pounds, but based on the way the scale operates, we can actually measure it down to about 10 or 20 grams of resolution on that scale. And if you combine this with the fast-acting valves and the other components in our system, it gets you to where your primary system, in our case, has an uncertainty of about 0.02 to 0.05%. That's a pretty low reading. We use this, in our case, we use this primary calibration facility to calibrate our bank of critical flow nozzles. So this is a secondary system. We determine the calibration coefficients for these critical flow nozzles by using our weigh tank system, and then we use the nozzles as our day-to-day operating calibration devices. And because we've stepped away from our primary system, our uncertainty increases a little bit. So now we're in the range of 0.05 to 0.15% of reading. And if you're not familiar with a critical flow nozzle, this is kind of what the inside of one of those looks like. Basically, you establish choke flow in the neck, in the throat region of that nozzle. And so you know area, and then you know the conditions of the plenum, and that makes for a very stable, not only a very stable flow rate, but a very stable system because it's just a mechanical device. Made out of stainless steel, it doesn't tend to change with time. So that's how we do things in our facility. So let's continue on the calibration path and talk about some things that you need to think about if you're going to send a meter to a laboratory. So one of the things that we looked at the start was meters that are sensitive to flow profile changes. So do you need to send just the meter, or should you send some upstream and downstream piping along with it? And then the next question is, how much upstream, downstream piping should you send with it? Another consideration is, how are you actually going to use the signal from the meter? Are you going to use a digital signal from the meter? Most modern flow meters have, Modbus output or some type of digital output that you can take into a flow computer to tell you what the flow rate is. God help you, are you going to use an analog? Are you going to use a 4 to 20 milliamp output in your system? If you can tell there I'm a little biased, you shouldn't do that unless you want not as accurate type flow. But the other type of quasi-analog output would be a pulse. So a pulse train is a very good way of doing output from most modern meters, and turbine meters all have that type of capability. And so then the lab has to interface to those devices as well. If you're pulling a meter out of the field, you might want to do as-found testing. So if your meter's dirty or has some damage to it, maybe you had a partial overpressure case on an orifice meter, and you want to measure what the error was from the bent pipe that resulted from that. You can do an as-found test and establish that. Or you've got a transducer that's failing in a multipath ultrasonic. Well, you can do an as-found test there that establishes how much error you might be incurring as a result of that damaged meter. And that may be a good thing for settling arguments with whoever you're trading gas with. And then, of course, you can fix the meter and then recalibrate it and get on with life. Scheduling is also kind of a big thing. As much as we love to do work for people, when people call us up and say, hey, can you fit my meter in tomorrow? Sometimes we can, but often we can't. It's not uncommon for a flow calibration facility to have 1 to 3 months of backlog or sometimes more. So, you know, plan ahead, work with your vendors to make sure that if you want the meter calibrated, that they've got that in their sites so that they schedule that with a lab ahead of time. It's always bad when, you know, the last thing is the meter's going to go out in the field, everything's built, everything's ready, and then someone says, oh yeah, we should calibrate it. And then, you know, either there's a delay or unfortunately it gets installed without it being calibrated and then you incur error. Different flow labs have different rules about witnessing tests. Lots of them can do it remotely. Gas industry is one that still seems to really like to do hands-on and look at the tests firsthand so they can see what's going on in the lab. Frankly, after you've seen one test in a flow calibration facility, you've probably seen enough. Paint drying is almost as exciting. But, you know, that's what we do. Happy to have guests see what we do. So when the meter test actually gets started, what's done? Well, the meter can be either shipped pre-assembled or it can be assembled at the flow calibration facility. Depending on the meter size and the length, you know, you may want to break it down to ship it back to its final destination as well. It can be kind of expensive to ship a very long assembly of a large meter type. When we build things up, typically we'll build things up from the upstream end to the downstream end. That lets us make sure that everything's aligned well, make sure we don't have any gasket material protruding into the piping, that kind of thing. Of course, the next thing that happens after the meter is built up is the meter is powered up, data communication is established. Instrumentation is another thing. Most calibration facilities have their own pressure and temperature references that they're going to use for your meter. Typically, you don't need to send your pressure, temperature, or DP devices with your device that needs to be calibrated. That simplifies things as well because it makes it easier for the lab to connect to their own devices and also to keep things in calibration. The specific piping configures, I mean, they really depend on the meter type. I'll give you a couple examples here before we start talking about actual calibration information. This is an ultrasonic flow meter. That's what the arrow says anyway. It's a multi-path meter. You can see the transducer sticking out. In this case, it's been installed with some clean-out tees that are used for inspection upstream of the meter. So this is a simulation of how the thing's actually going to be installed in the field. The difference here is it's probably going to be sitting on a header, not directly on these little elbows that lead into the inspection tees. So that's one difference that might occur between this installation and the actual field installation. But at least you're capturing some of the last effects of the piping installation before going into the meter. And that can be important. If you really want to be, you know, thorough, here's a skid with 3 meters on it installed in our facility. You have a 6-inch and an 8-inch ultrasonic meter that bracket either side of a 3-inch rotary meter. And this particular installation includes all of the headers, includes the valves. I mean, this is the whole deal. So, you know, the calibration that you would get out of this type of test is probably going to be pretty indicative of the performance of the meter in the field. You're probably not going to have too many surprises when you put this meter in the field, or these meters actually in the field. Okay, so I showed you some ultrasonic meter examples. So let's talk a little bit more about multipath ultrasonic meters and talk about the actual process of calibrating a meter and then the outcome of those calibrations. And since we're meter agnostic here and manufacturer agnostic, I've got a bunch of different multipath meters there. You can pick your favorite and you can dream that the data that I'm going to show you applies to one of these. The details that I'm going to go through here are pretty similar for any meter type. I'm just going to talk about ultrasonic meters for this part. With any meter type, what you're going to do after the meter is installed and ready to go, all the calibration facilities are going to do this. They're going to start the flow up. They're going to flow through that meter at whatever pressure and temperature condition they're going to test at. And they're going to do that for long enough to ensure thermal stability of the meter, the pipe, everything around it. That tends to be one of the longer parts. Getting ready to test is just waiting for things to kind of settle in. If you're doing an ultrasonic meter and you're doing it for AGA9, AGA9 has some specific recommendations for flow rates that you should test at. 100, 75, 50, you can see the number there, down to 2.5% of full scale. It's kind of the logarithmic scaling type test set there. Of course, you don't have to do that though. Those are recommendations. If your meter is always going to operate at 70 feet per second or 60 feet per second, you should probably calibrate it in that range and be happy about it. Characterize the range that's going to matter to you the most. If you're going to utilize the full scale range of the meter, then by all means calibrate it over the full range. We know some people that calibrate it past the full range just in case. That way if they have some event where they need to go beyond the quote-unquote full-scale capacity of the meter, they can do that as long as the meter tolerates it. So you're going to test at these different flow rates. For each of these flow rates, what we do is we take multiple data points. So that's how we get some of our uncertainty information, our repeatability information, by taking multiple flow points. In our case, typically 3 to 6 measurement points. Each of those measurement points is going to be anywhere from 90 to 300 seconds long. And we're going to average those values out over that period and provide a point that says, that characterizes the meter at that flow rate. Typically, we're going to do that from high flow rate to low flow rate. That tends to keep facilities more stable when you do it in that order. For an ultrasonic meter, we're going to record the path by path and other diagnostic information. We're going to hook up the meter's manufacturer software to that meter. We're going to take our data with our system, but in addition, we're going to record log data, diagnostic data, using the meter manufacturer system. That's really important for later on. It helps establish a baseline for the meter that you can use first when you install it in the field to make sure that the meter's still behaving as it did in the lab. And then it also forms a reference for you for later on. So when you come back 3 months, 6 months, a year later, you have diagnostic information to compare to. How is that meter performing? Is it still doing what it did when I first installed it? If it's not, well, then there's probably something you need to check. The other thing on an ultrasonic meter that's useful for diagnostics is that you can compare the speed of sound that the meter reports to what you can calculate based on your composition and your pressure and temperature. And those values would come from now AGA 8. It used to be AGA 10. That's been eliminated. But AGA 8 allows you to do those calculations as long as you know the gas composition, of course. Okay, so you've collected these points at these different flow rates, and now you want to adjust the meter so that it best matches the reference, the flow calibration facility. And in the case of an ultrasonic meter, AGA9 allows 3 different common methods for correcting the meter output. You can use what's called a flow-weighted mean error correction, a polynomial error correction, or a multi-point linearization. By far, the multi-point linearization is what people use these days. The other methods are really in there kind of grandfathered in. Because when meters first came out, the electronics didn't fully have the capabilities of doing other types of corrections. So the thing is, depending on how the meter curve looks, one of these methods may be better than the other. If you have a really good meter and it's flat, it truly doesn't matter which one of these methods you use. But meters typically have a little bit of, we'll say, funk to them, and leave it at that. Different meters have different behaviors, so it's best to figure out what correction will work for one. Let me show you an example of a flow-weighted mean error correction. And this is awesome because it moved my line. Different computers project things differently. That dashed line is supposed to be at 0, not at -1/4. But what you see is as found data here, let me get my mouse going here, is a diamonds. If I do a flow weighted mean error correction, basically all I get to do is shift the entire curve up. I'm going to weight it more heavily towards the high flow rate points. That's what the flow weighting does. So you can see that at the higher values here, I'm only off by, I'm still high, but I'm only off by about 1/4%, versus the low end points where I'm still off by maybe 1% or more. This isn't necessarily the best way of correcting this meter, because it still leaves me with error, and I don't want that. This is just how the flow weighted meter calculation is done, how it's converted into a meter factor. Another method is a polynomial correction. Basically, it's a curve fit, okay? So if I do a curve fit, then I still end up with some residual error that you can see here. These points get shifted up to there. That's my residual error that ends up after the polynomial curve is applied. But you can see I've better characterized the entire range of the meter. The other thing that I've done is I've smoothed the meter out a little bit. You can see how the points kind of are up and down along that polynomial line there. And so the question is, how much of that is an artifact of the testing versus how much of that is really the meter doing, presenting that information that way. So polynomial actually can smooth out some of that information. Of course, everybody who knows about curve fits knows the danger with a polynomial is you don't apply it outside the range of the data, because polynomials do crazy things sometimes when you try to extrapolate. So that's one of the downsides with polynomial. As I mentioned, point-by-point linearization, this is the most common way of doing things these days. And basically, you take each point and you shift that point so that it becomes a zero. So basically what I'm doing is I'm drawing a straight line between each and every one of these calibration points. And in this case, you can see the black squares just barely. Those are the points that were done after this point-by-point linearization was applied to the meter. So you can see that it did a pretty good job of moving the meter to where you would expect it to do, and then we actually verified that. The thing about a point-by-point calibration is you're interpolating in between these points, so if there is something funky that happens in between points, you don't necessarily know what happened there. None of the other methods will show you that either. This one will interpolate, though. The other thing that can happen, though, with a point-by-point is you can do what's called, you can fossilize behavior into the meter. These little bumps where you can look at this point and say, well, gee, that point should be a little bit lower. Well, that's what the calibration facility came with, right? It could be due to uncertainty, it could be something with that particular point, it could be that that's truly in the meter. You don't know. But once you do a point-by-point calibration of that meter, that's how that point is always going to behave. That's what I mean by fossilizing it. You've captured that in the meter. So if it's real, great. If it's not real, oh well. As I indicated, if you have a flat error curve, any one of these methods is going to be good. I think I've said most of this stuff already. The best answer depends on the curve behavior. Let me move on because I'm taking longer than I thought I would. Angel's smiling because I'm just doing such a fantastic job and you guys are enjoying this to such a degree.
I can tell by their silence.
Yes, it's obvious. Whenever you do a calibration report, AJ9 recommends items that have to be included in that report, documenting the procedure, documenting the setup. Basically, it's a lab report, right? So anything that was there to let you reproduce that test should be included in that meter documentation. And again, this is going to be true for other meter types as well, just specifically is called out in AJ9. Okay, so an Orifice flow meter. Everyone knows an Orifice flow meter. You've got an Orifice plate, you've got pressure taps on either side. You built this Orifice meter run to AJ3 or to API 14.3, it's the same thing. And you expect that that answer should be right. It should be within a certain uncertainty band that's presented in that report. Well, that's true, but you can actually improve the performance that you're going to get out of this meter by doing a calibration. And what I'm showing here is a calibration curve. It's the discharge coefficient versus Reynolds number for a specific meter. That discharge coefficient basically is proportional to the flow rate through the meter. So it's a measure of the meter factor, if you will, of the meter, if you're not familiar with Orifice meters. The Reynolds number, that's the x-axis, that's basically the flow rate. It's got some other terms in there that account for pressure and the density of the fluid and that kind of thing. If I go to AGA3, I'm going to get this black line. That's what the discharge coefficient should be, according to AGA3 for this particular meter. But this is what I got. Now, it's not that far off. It's still within the red and green bands that are the limits of uncertainty for that type of meter. But you can see that I also have a little bit of separation between the taps on the top and the tap on the bottom, 0.15% separation. Is that a big deal? I don't know. How much money are you putting through that meter? Are you measuring it on one tap and the person you're exchanging gas with is measuring on the other, and you disagree because that's just how the meter calibrated? So you can see there's a slight difference there, and then they're both slightly off of the accepted line. So you can improve this meter's performance by calibrating the meter and using the discharge coefficient that comes from a calibration. And if you do that over several hundred meters, which is what I'm showing here, and you just calculate what the error is relative to the acceptable bounds that are in AGA3, you can see that sometimes they're not within the bounds of the document. The meter tubes are all made within the specs, but the results are not all within the specs. And this is a combination of meter plate and meter tube. It's not that we're a really bad lab and we just can't get the answer right. It's because there's a little bit of bias. In our case, a lot of these meters are tested, they're of a certain range where we can demonstrate that there's a bias in the AGA3 equations. And you can see they're all a little bit high, about 0.25%. But the idea, though, is that even though an Orifice meter doesn't have to be calibrated, you can calibrate it and you can improve the performance. That's the takeaway here. And it's a combination, too, right? It's a combination of the meter tube and the plate that need to be calibrated so that you can reproduce this when it's installed in the field. If I have the type of meter fitting that I showed you in the first slide where it's a dual chamber fitting where I can replace the plate, calibration isn't going to make a lot of sense unless you're going to calibrate all the plates you're going to use. You would need to do that. Okay, moving on a little bit. Turbine flow meters. I mentioned some turbine flow meters are susceptible to flow distortions and some are not. The ones that are less susceptible look like the turbine meter on the left. They have a flow conditioning device in front. They have a narrow annulus that accelerates the flow. They have a tapered tail on the back that helps to recover the flow. So it's a low pressure drop device. If I have the meter type on the right with a more wide open design, wide open annulus, I'm not really conditioning the flow as much. I'm not trying to recover the flow. It's not that these are bad meters. They're not. They just require a little bit different flow conditioning entering the meter than would the meter on the left. So if you have the meter on the right, you're probably going to want to ship the upstream piping, the flow conditioner, all that stuff with it to make sure you get the right answer. If you got the one on the left, you're probably not going to be as susceptible to those types of changes in your meter run. So a turbine meter, though, you can look at this, and this is an example of an 8-inch meter relative to a single K factor. So the K factor is the pulses per cubic foot produced by that rotating set of blades. And if I characterize this meter with a single K factor, I'm not going to get the best answer in the world. This is kind of similar to doing a flow-weighted mean error correction on that ultrasonic meter. You can see that I'm going to have points that are high and points that are low relative to that average error curve. In this case, I can do a point-by-point characterization, and that's going to eliminate some of those errors. And typically, that can be built into the flow computer that you're interfacing this turbine meter to. Most flow computers have that capability to build a table of K-factor versus flow rate or error versus flow rate to help solve that issue. The other thing that you might want to consider is what pressure are you testing at. This is an example of a 4-inch meter tested at atmospheric air, that's the curve down here, and then tested with natural gas at elevated pressure. And you can see that there's about almost a 2% shift between the meter's behavior with atmospheric air and 150 psi natural gas. Turbine meters, there's an initial shift that occurs with turbine meters with pressure that then stabilizes as you get to higher and higher pressure. That's one of the reasons why turbine meters, it's recommended that there should be characterized as a function of Reynolds number, and really, if you can, do it at the operating pressure to help reduce the uncertainty. The other thing is, use all your data. So use that multi-point linearization that you can get out of the calibration to minimize the error curve. And I already mentioned the piping thing. We're getting towards the end. I'm accelerating here. Sorry for spending so long on the first parts. Coriolis Flow Meters. So here's some different design Coriolis Flow Meters. Again, pick your favorite, or if your favorite's not up there, I apologize. But you can calibrate Coriolis Flow Meters on gas. They're always calibrated on liquid by the manufacturers as well, and that's great. When you calibrate them on gas, sometimes you can see slight differences. And again, it's about removing that last little bit of uncertainty by calibrating the meter. Here's an example of a meter calibrated on gas, 5 different flow rates. The bounds that are there are the AGA11 bounds for a meter. And you can see, in this case, if I can get my mouse to work, that I've got about 1/4% uncertainty or 1/4% error in the meter relative to my reference standard. And I can adjust that out. I can put a meter factor in there and take care of that. The other thing that I want to show you, though, on this plot is those red dots up above. What are those? Those are the dots that I get if I don't put the pressure compensation into the meter. Coriolis meters are like a big balloon, okay? As you put more pressure in that balloon, it gets stiffer. That changes the response of the balloon or the Coriolis meter to flow. So it's important to compensate that meter for pressure if the meter manufacturer says that you need to do that. Some of them have different methods of doing that where they try to measure things and compensate for them using strain measurements. But if you have a meter manufacturer that says there's pressure compensation needed, you should activate that because it's going to improve the accuracy of your meter. And you can see with that we got to this 1/4% number. If we hadn't done anything, we would have been 0.5% high to start with. We adjusted it, that makes 1/4%, and then we can further adjust the meter to make it match our facility. The other thing that's important about Coriolis meters is you have to zero Coriolis meters. The zero on a Coriolis meter is what becomes the reference for that meter's behavior. Typically in a lab, what we do is we flow through the meter, again, get that thermal stability, get everything nicely soaked, and then we shut off the flow and we tell the meter to self-zero. That forms the reference for the meter so the meter knows what zero flow is. If you don't do that, you can get results like what are shown here on the red dots, where as you get lower and lower in flow, your error will increase higher and higher. That's because that's the effect of that zero flow offset. In this case, you can see if we correct the meter for that zero flow, again, my screen differences are awesome here. I have a dashed line here that's below 0. That's supposed to be at 0. You can see that the results come much closer to the 0 line. Calibration notes, I just said zeroing is important, pressure is important. Coriolis meters, some manufacturers now also include the multi-point linearization. All of them include a single factor linearization. Like ultrasonic meters though, Coriolis meters have diagnostics. You should record those. The gain levels, that kind of thing need to be taken into consideration so that later on you can tell whether the meter is still working properly. And like AGA 9, AGA 11 that applies to Coriolis meters, has a whole list of items that you should include in a calibration report. Okay, so conclusions here. Hopefully you see that the basic method, it's independent of the meter type. You need to understand your end-use accuracy requirements, understand how much of the meter assembly that you need to ship to the lab, assuming that's what you're going to do. Keeping in mind calibration facilities, this is what we do for a living. Any of the guys at the other labs as well, they absolutely are more than happy to help you understand what the best practice is for the meter type that you have and can help you make those decisions. Calibrating the meter is obviously going to reduce your system biases, and basically the idea is it's going to get you the right answer. Calibrating the meter before you install it, even if that meter is only off by 0.1%, you didn't know that unless you calibrated the meter. So it's a good verification of proper behavior of the meter before you install it in the field. If you don't calibrate the meter and you have a problem, that's going to be one of the first places you look and you say, what's wrong with that meter? Well, I didn't calibrate it, so I don't really know. And that, I think, is my last slide. And I left you guys like 37 seconds for questions.
I've got 3 minutes on my clock.
Okay.
But, everyone did call in, and so if you need to drop off the call, that's it's up to you to do that. But we do have 3 questions to go through, so I will ask those now. Let's see, where is question 1? 2, all right. Okay, first question is, are there industry papers available to compare the uncertainty resulting from the following 2 flow calibration techniques? First one is a mass-based calibration system. It has to be converted to actual volumetric flow via an equation of state. The second is a test facility that, quote-unquote, bootstraps from a master volumetric standard through transfer standards to the place of calibration.
Yeah, I have not seen, I'm not aware of any papers that directly compare those 2 methods. I'm aware of those 2 methods because we use one, and we use the mass-based method to calibrate our system here. Most other places in the world actually use the bootstrap from volumetric devices, the rotary meters, to take it forward. There are definitely papers out there that describe that bootstrap method, and there are definitely papers out there that describe the mass calibration method, but papers that contrast and compare the 2 that says which one's better or worse, that I have not seen.
And you did mention that there's a, each lab creates a report of their uncertainties. I guess if you compared those 2 facilities, what they report, would that be the answer?
That's part of the answer, because it depends on the implementation of those 2 methods, right? I think the question was which of those methods, the underlying question is which of those methods is better.
Yeah.
And the overarching answer is, of course, it's an engineering answer, so it depends. It depends on how you implement those 2 and what the uncertainties are associated with the individual components that are going in that and how you bootstrap it versus how you do the mass flow. So it's not quite as simple as just saying one's better than the other. Okay.
Thanks. I'll move on to the next question. And the next question is about finding as-found data for calibration on a flow meter. How important is it to send the whole setup of the meter, including the flow conditioners, elbows, and other things, to the calibration lab?
If you're trying to do an as-found test, that's extremely important. If there's some reason why you can't send the exact components to the lab, you should work with the lab to see what they can do to simulate the configuration that's there. Typically, if you're trying to do an as-found test, if you've got enough concern to do an as-found test and you're eliminating really any part of the setup, then you're probably not doing a true as-found test. The experience and measurements have shown that it's typically not just the last component before the flow conditioner or the meter run that matter. headers, upstream valves, other items that are further upstream than you might think can also influence the results that you'll get at the meter. Disturbances propagate lots further than you think, even with flow conditioners in the line.
Yeah, thanks. And I'd like to point people also to the webinar that Jim Whitty did for us about a year ago now on gas flow measurement in lower pressure systems. And so that's available. If the link for that was on your invitation. So that has a lot of information about flow meter setup things.
Yep.
So the third question was, what if, is there any sort of a hybrid curve fit, like a polynomial with a point by point, and if there is it acceptable with AGA 9?
I'll answer the second part of that before the first. Is it acceptable with an AGA 9? I think, AGA 9 has recommended methods. People tend to look at that document and say that's the only thing that's allowed. And that's really not how most people, at least in the U.S. gas industry, interpret that. And certainly the intent of the committee was not to eliminate something that might be a better way. Usually the question is, will your customer, will the person on the other side of the fence accept your cool multi-point curve fit thing that you're going to do? The other part of that question is, does that exist? I haven't seen it directly, but I can't see why it wouldn't. If you can establish from basic physics what the shape of the curve should be between 2 points, it makes perfect sense to apply that curve shape between them so that it's not, say, strictly a linear interpolation. If you know that the meter behavior is second order or something like that, then that makes complete sense to do that. And that's kind of why I was alluding to the idea that I don't think the AGA Transmission Measurement Committee that produces AGA 9, I don't think that they would say that that's not allowed if it's a good method. You just have to justify it to whoever you're dealing with.
All right. All right, well, that was all the questions I had. So I want to thank you very much. And we're only 3 minutes over, so I appreciate everyone stuck around. And join us for the next webinar. Thank you very much.